Okay, so I'm going to do a quick construction of what's called a Hopf-von Neumann algebra. And what this does is that we take a W star algebra, or a von Neumann algebra, and endow it with a Hopf structure. But first we're going to start off with a Lie group and its Lie algebra, which is the tangent space at the identity of that group. And then from there we're going to construct the Hopf-von Neumann algebra. Okay, so here's a Hopf-von Neumann algebra construction. We start out with a Lie group, which is a group and a differentiable manifold simultaneously. So we'll start with this little thing here with these little holes in it, for example. And this thing here, G, is called the Lie group. Now, somewhere along this manifold, we can endow it with what's called an identity element, right? And let's say the identity sits right there. It looks like a little sad identity. Let's fix that. That's the identity element that we're choosing. This is an arbitrary representation. This manifold can be in some arbitrary dimension, but at this identity element, there exists a tangent space. This tangent space, which we'll label T sub I of G, the tangent space at the identity of the Lie group G, is equal to this thing called a Lie algebra, which is the derivation algebra of the Lie group G. Okay. So now that we have that information, we know that a Lie algebra is non-associative and non-commutative. The non-commutativity we're not worried about. It's the non-associativity that's holding us back in terms of defining powers over vector fields defined in the Lie group G, or the Lie algebra G. And we'll assume that the vector fields in G here are left invariant. And so if we have the tensor algebra of a vector space V, well, a Lie algebra is also a vector space, so let's replace this vector space with the Lie algebra right here. And so this tensor algebra of the Lie algebra is the direct sum from 0 to infinity over all n of the nth tensor power of the Lie algebra G. And so now we have an associative algebra with this generally non-commutative product called the tensor product. And so this gives us a base field, such as, say, the complex numbers, direct sum with the first order of the Lie algebra, which is just G, direct sum now with the second order term, which is G tensor G, direct sum, so on and so forth up to infinity. So this is just, for example, the 0th tensor power of G, direct sum, the first tensor power of G, direct sum, the third tensor power, or the second tensor power of G, direct sum, so on and so forth. Okay, so now we have multiplication defined in an associative way here. This is really nice. Now, this tensor algebra G, we want to compose and bring back the Lie bracket concept that's available to us in the Lie algebra G. And that Lie product, the Lie bracket, is given by that symbol right here, this little bracket here with two inputs. So we can take an ideal, we can quotient out an ideal, something that goes to 0 within the quotient called the ideal. And let's choose that ideal. To be generated by x tensored with y, where x and y are elements of the Lie algebra G, minus y tensor x. So this measures our non-commutativity here, and then we subtract from that the Lie bracket of the elements x and y. Now, since the ideal goes to 0 inside of this quotient algebra, we find the following situation. X tensored with y minus y tensored with x minus the Lie bracket is equal to 0. And so now we can define the Lie product, the Lie bracket, in terms of the tensor product difference here. So we have x tensored with y minus y tensored with x equals the Lie bracket. And this is a generalization of the canonical commutation relation in quantum mechanics. Okay, so that's pretty nice. What can we do now? Because, well, first and foremost, what is this quotient algebra of the tensor algebra? Well, we're going to quotient it by this, and then we have the Lie bracket defined in terms of this non-commutative measure of the tensor product between elements in the Lie algebra. This algebra here, this whole quotient algebra, is called the universal enveloping algebra of the Lie algebra. Because since here G is defined in terms of left invariant vector fields on this manifold, we have the left invariant differential operators on this manifold, this group here. And that's pretty cool. And we'd also want the right invariant differential operators. And what's important to note here, by the way, is that the center of Z gives us the Casimir operators, the bi-invariant differential operators. They don't distinguish between left and right invariants. These are bicovariant in a coordinate basis, if you will. But this is also isomorphic to the center of the opposite universal enveloping algebra, where this G-op, the opposite Lie algebra, refers to the fact that we have an opposite multiplication defined on it. So A with the opposite product in B is equal to B times A. In all other ways, though, it's similar to the other universal enveloping algebra. And so now we have the universal enveloping algebra on the Lie algebra, which is just the left invariant operators, but we also have the universal enveloping algebra on the opposite Lie algebra, which are the right invariant operators. And if we want to compose these together while also maintaining the center of these, well, we don't want to double count the center because we want to have the bi-invariant operators with the left and right invariant differential operators. But we don't want to double count them. And on top of that, if we want to combine the left and right together into a single algebra, well, we might say, for example, let's say we have an associative algebra A, and let's say we take the universal enveloping algebra of the left invariant vector fields generated under the Lie algebra, and we tensor that with the opposite. Well, now we have a case where, like I said, we're double counting now the bi-invariant differential operators because they both exist in the center of both of these. But the problem is we have this tensor product here. And so now we have the center of this and the center of that appearing like they operate on the left and right side of the tensor product respectively. And so that's not really a center anymore. So the center of each of these algebras is no longer the center of this entire associative algebra here. But we do indeed have the left and right invariant differential operators on the Lie group here. But we have two copies now of Casimir operators, and neither of them are actually a true center of the whole algebra. So how do we get all of that into one algebra without this double counting issue? Really simple. We take this structure here and take its bicommutant. We grade it by the elements that commute with the elements that commute. That's called a bicommutant, or a commutant of the commutant. And with this information, we take just those elements of these two algebras. This is called a von Neumann algebra, M, also called a W star algebra. Now we want to have a Hopf structure imposed on this, a Hopf structure. Because we want to encode not just the left and right invariant differential operators with the Casimir operators at the center, But we want to do it in a way where not only do we have the collection of that, but we want to have all their interactions as well as the ways they can possibly be deformed in some type of sense. And we can compose this into a single algebra of all invariant operators on the Lie group without breaking any of our math here. So here's what we do. We define what's called a coproduct, which maps us from the von Neumann algebra M in this case to a weak tensor product inside the von Neumann algebra. But then we also have what's called the coproduct, and if it acts on, let's say, an element x, it just gives us 0. Same thing with y, if y is an element of the opposite Lie algebra. But even better here, we have what's called an antipode on some, let's say, an element x of either one of these algebras that gives us negative x. Now we've imposed a Hopf structure in here, a bialgebra structure. And when we take the collection M with delta, with S, and epsilon, the antipode, and the co-unit, with the coproduct, all of that with the von Neumann algebra, we get what's called a Hopf-von Neumann algebra. And that's our construction.